Welcome to another riveting installment of Pre-Calculus from Home. Today's exciting topic is section 6.5, Trig equations. This section is very closely related to section 5.7, which hopefully you've just finished up watching some videos about that, so that's fresh in your mind. Except it's going to be different in some key ways. And to illustrate that difference, I'm going to use this. On the left, we have x squared equals 9, an equation. On the right, we have x equals the square root of 9, another equation. I would like to solve these. On the surface, it looks like these two things are fundamentally the exact same equation. They probably should have the same solutions. Let's see. The square root of 9 is 3. So this looks like the answer should be x equals 3. Here, I can solve this by moving the 9 to the other side and then factoring. This is the difference of squares. I get x plus 3 and x minus 3 equals 0. So x equals 3 or x equals negative 3. It turns out these two equations are not the same. They have different solutions. Here, this symbol, the square root symbol, the radical, always means the positive square root. That's why the solution here is 3 and not negative 3, because this symbol is sort of range restricted to only the positive values. Here we don't have that symbol. Nothing is range restricted. I can find any x value that satisfies this equation, and the x values that satisfy this equation are 3 or negative 3. Here we have two solutions. Here we have just one. They are very different equations. Well, perhaps not very different. They are certainly different. With this in mind, I'm going to draw another couple equations on the board, and we'll see what we think of them. Oh no, the blue does not erase very well. That's a shame. Such a pretty blue as well. Maybe if I use this, it will erase? Oh, that's much better. Okay. So, keeping in mind the distinction between x squared equals 9 and x equals the square root of 9, let's take a look at another couple equations. On the right, I'm going to say the sine of x equals negative root 3 over 2. And on the right, I'm going to say arc sine of negative root 3 over 2 equals x. Once again, I have two equations here that on the surface look like they should be identical. But in practice, these two equations are very different. This 5.7 videos talk at length about how the arcsine needs to be range restricted so that it can be a function. This has exactly one solution. The only x value that has a sine of negative root 3 over 2 that is in the range of arcsine is negative pi over 3. This has exactly one answer. There's no comma or, there's no list of answers, there's no other options. This is the only correct answer to this equation. This, as written, has no range restrictions. So I could say x equals 4 pi over 3 or 5 pi over 3. These are probably the two angles that you will find on your unit circle that get associated with this. So these are two good options. We can also look at things that are coterminal with this. So I could add 2 pi to either of these numbers. I could get 11 pi over 3. I could get 10 pi over 3. I could get 17 pi over 3. I could get 16 pi over 3. This is me just adding 2 pi to all of these things. I can add 2 pi forever. I'll use some dot dot dots to express the fact that this list keeps going. So here's 6 answers so far, and none of them are this answer so far, which means if I want to get that answer on my list, I need to start going backwards as well. Negative pi over 3 is what happens when you subtract 2 pi, and you can keep going backwards that way. If you subtract 2 pi here, you can add negative 2 pi over 3 to this list of answers, and you can keep going in that way as well. So now there's 8 answers to this equation, and there's lots more. I chose to stop here because I'm running out of room, not because I ran out of answers. This equation has infinitely many solutions, which is why the arc sign is pretty nice. We only have to deal with one of them. Just find the correct one from among the infinitely many possibilities. We have rules for deciding what the correct one is when the word arc sign gets involved. But if the word arc sign does not get involved, we have infinitely many answers. So there's 2 things we're going to do to sort of address this problem when we're dealing with trig equations and there's no arc signs involved. And yes, there's not going to be any arc signs involved in the homework for this section. It's all trig equations. The 2 things we're going to do to solve this problem are, we could find a way to express this infinite list of possibilities in a concise way that doesn't use dot dot dots. I said earlier that these were the 2 solutions that naturally appear on the unit circle. The unit circle, probably, if you're looking at the same unit circles that I'm looking at, it contains angles between 0 and 360, which is 0 to 2 pi in radians. These are the 2 options that are in the range from 0 to 2 pi. So those are sort of like the base starting point solutions to this. From these 2 solutions, we can get all the other solutions by adding 2 pi, adding 2 pi again, adding 2 pi another time, or subtracting 2 pi. You can subtract 2 pi. Which means that the concise way to express the answers here are starting value, 4 pi over 3, plus a multiple of 2 pi. N can be any integer. Let me finish writing this and then I'll talk about what that means. Is that on the screen? No, it's not. Of course it's not. Back this up. Now is it on the screen? Okay, here we go. So, again, these are my 2 sort of starting values, because these are the 2 that appear on the unit circle. These are the 2 that are in the 0 to 360 range, 0 to 2 pi range. And you can get this entire rest of this infinitely long list with this clever little trick right here. You add 2 pi n. If n is 0, that means you're looking at the basic solution. If n is 1, then you've added 2 pi once. If n is 2, then you've added 2 pi 2 times. If n is negative 1, that means you've subtracted 2 pi and you're over here. If n is 10, that means you've added 2 pi 10 times, and that's still a solution. any integer multiple of 2 pi added to either of these base solutions will give you the full list of possible solutions for x in this equation. And we usually add a little note here. We say, if we're going to add 2 pi n, we'll say n is an element of the integers. Let me write this more clearly. This symbol, I've been using it for a couple decades now. I still don't know if it's supposed to be like a round E or a C with a line through it. Not sure. But it means is an element of, and this symbol is called a double struck Z, and it means the integers. Oh, I know how to spell integers. So, as long as n is an integer, adding 2 pi n will get you coterminal angles, and now this is a concise way to represent the full list of solutions to this problem. I mentioned that there were 2 solutions we were going to use to solve this "these lists are infinitely long" problem. And the other solution we're going to use is sometimes the problem will just come attached with a range restriction. So sometimes you might get things that look like this. The sine of x equals 1/2. X is in the range from 0 to 2 pi. The 0 will get a bracket here because we want x being equal to 0 is something that we want as a possibility. 2 pi will get a parenthesis here because x being equal to 2 pi is not something we want. 2 pi is coterminal with 0, so we only want to include one of these endpoints, and 0 is the one to choose. This might also look like 0 is less than or equal to x, which is less than 2 pi. So sometimes you'll get these problems and they'll have range restrictions attached to them. And at a glance, those probably seem easier. We can just say, if I only have to worry about the x values that are between 0 and 2 pi, I can just say x equals, for a sine of 1/2, pi over 6 probably is one of them. What's the other one? 5 pi over 6? So these are the 2 angles on the unit circle that will produce sine values of 1/2. So if this thing is range restricted, your list is going to be a lot shorter, a lot cleaner than this, which is nice. But there's a problem. These things are going to get more complicated. So I'm going to go into that in the next video.